share.
Yeah.
My everything is off here. All the sounds are off.
Sound is off. Speaker is off. But so your this mic will pick up.
Yeah. Okay. Okay.
So you are live now. Understood. You actually switched off your video.
Yeah. Is that okay? Or?
No, I mean you can switch it on.
I can.
No, switch it on. These lights are switched off. These ones. Yeah.
So, welcome to today's lecture by Jyotishman Bhowmick. Jyotishman is a person who studied at Indian Statistical Institute and later on joined the same organization to work as faculty. He is a grad student of my advisor, so that's our lineage. And
You're his uncle.
huh?
You're basically his uncle.
Yeah, academic uncle. So that's where he gets to work. And long ago, Alan Kahn invented a language which humans don't understand, a language called non-commutative. So he is one of those aliens who understands it and is not talking.
Thank you so much for the invitation. It's been really nice staying here. So, so our goal today is quite modest. So we will be we will try to understand what.
That's fine.
Yeah, yeah, I think it's fine. So, what it means to be a geometric data for a non-commutative ring. So basically, so this subject is about the study of non-commutative algebras by imitating techniques from a differential geometry. So we will first give some examples of some relevant spaces. Then we will give their sort of quantum or non-commutative analogs, and then we will sort of revise what's meant by a geometric structure on a level surface, and finally we will define the what's meant by a differential calculus for a non-commutative algebra. Okay, so I will start with very basic examples. Of course, I mean this might be sound very trivial. So the first example will be the circle. So in the abstract, I mentioned that my that these relevant spaces will be level surfaces, which means that they are common zeros of a bunch of polynomials. So in this case, so I have the function R2 to R given by f of xy is equal to x squared plus y squared, and then so S equal to f inverse of 1. So in this case, so I have a single polynomial, and I am looking at the zero set of f minus 1. So why is this special? Because the df(x) from yeah, so if you look at this map, so T fx of R, so this has full rank for all x in f inverse 1. Okay, so this I will again come to the fact why I need this. So basically, this is the reason why the circle is a nice.
What is dx of two?
Oh, so thank you. Yeah. So the tangent space at the point x. Okay. Okay. So basically, so this rank condition makes circle into a manifold. And this gives it a smooth structure. And then once it's a manifold, meaning that it's locally Euclidean, so then I can define the smooth functions on it and vector fields on it. So
small x is coordinate point in R.
yeah. Thank you. Yeah. So the next one is a torus. So in this case, we will see. So look at R4 to R2. So again, so df, sorry. So f of x1, x2, x3, x4 is equal to x1 square plus x2 square, x3 square plus square. So then the two torus is the inverse image of 1, 1. Okay. So again, I have the full rank condition, which makes it into a locally a Euclidean space. So and then, well, I mean, so there are of course lots of examples, but I will only give some of them. So next, you have the SU2, which is the set of all of 2 cross 2 complex matrices which are unitary and having determinant 1. I have the okay, so and then okay, so I have SU2. I have the orthogonal matrices. So these matrices have real entries and they're orthogonal. And I also have the two sphere. So we all know this guy. So the thing with so all of these are actually examples of level surfaces, by which I mean the following. So definition. So an n surface in Rn plus k is a set S in Rn plus k of the form S is equal to F inverse of C, where F Rn plus k to Rn is say infinity, and sorry.
You want an n surface. So. Oh no, it's
Yeah, it's a Rn, right? Yeah. So so the co-dimension is K. So and so number one, so dfx has full rank, and yeah. So what follows is that and then I have a theorem which says that so any n surface wait, yeah, I think yeah. So basically, my so let's just check whether I did it wrong. So so kernel dfx. So that's basically the tangent space of S. So full rank means that the yeah. So thank you. Yeah. So any n surface in Rn plus k is locally Euclidean, meaning that that is there exists P. Okay, so that is given P in S, there exists U open. So U contains P and phi U to phi U contained in Rn. So which is open. So this guy is open in Rn, and this phi is a diffeomorphism. So locally, my set looks like some Euclidean space, and that's what helps me to develop my calculus, and then the notions of vector fields and geometry. Okay. So just yeah. So a remark. So this n is called the dimension of S. Okay. 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 So we have seen what we mean by spaces or relevant spaces in our context. So let's get some examples of rings, which will be of some interest to us. So before I give the examples, so just let me point out that our rings will be a bit special. So they will have the ring structure as well as a vector space structure, and both these structures will be compatible. So here is so an algebra, and all my rings will be over the complex numbers. So is a complex vector space A such that A is also a ring. B, so I have the compatibility between the ring structure and the vector space structure. So things like this will hold. Okay, this is how chat. Smooth variety. Yeah, so is that a
I think he needs a smooth variety is what I'm saying.
yeah. Okay, so let's look at the first example. So I had so my classical examples were the circle, the torus, SU2, ON, and S2. So, okay, so let gamma be a discrete group. So then the group ring, so this is defined to be symbols like this. So finite sums, so gamma in gamma, but finite sums. Yeah. So this is a vector space. So the basis is given by the symbols lambda gammas, and the ring structure is actually given by the group law. So as you can see, so any element is a linear combination of these lambda gammas. So these a gammas are just complex numbers. So in order to define a ring structure, it's enough to define it on this lambda gammas, right? So I need to define lambda gamma times lambda gamma prime. So I will simply define it by lambda gamma dot gamma prime. But this dot is the group multiplication. Yeah. So I am for the moment I am just using it as a symbol. So I mean, if you want, you can also write just gamma instead of lambda gamma. But yeah, I mean, it's at the moment it's just a symbol. But this particular notation comes from the fact that these lambda gammas can be seen as linear maps from square integrable functions on gamma to itself. If I find time, I will come to it. So yeah.
Addition gamma plus gamma, that's just itself considered as a
Yeah. So yeah. So just addition is just component wise. So okay. Before I end this, I will just make one comment. So yeah. So remark is that gamma abelian if and only if the group ring is commutative. Okay. So as soon as gamma becomes non-abelian, I have an example of a non-commutative ring. So the second thing is that, so if gamma is equal to Z, then C gamma, so this is equal to the algebra generated by 1 Z star. Yeah, I mean subalgebra. Subalgebra of C of S1. It's easy to see this. I mean, if in case you were wondering. So basically, the map is okay. So CZ to this algebra generated by 1 Z star. So the map is given by lambda 1 goes to Z, lambda minus 1 goes to Z star. Okay. Now, since CZ is just as a ring, it is generated by lambda 1 and lambda minus 1. So this actually extends to a ring homomorphism from CZ to that guy on the right hand side. Okay. So this is why I wanted to mention it as a as an analog of S1. So it gives more examples.
Z star will be 0, not Z0.
Huh?
Z star will be 1.
Yeah. So all these lambda g's, so they are all what we call unitaries, because lambda g star is actually is equal to lambda g inverse. I mean, I have not defined this. I have not defined the star structure, but yeah. Okay. So I am not doing very well in terms of time, but okay. So so the next target is to define the non-commutative torus, but before that, I will just need to introduce some. Yeah, I mean, just introduce some known functions. So basically, what we want to do is that out of the smooth functions on the torus, we want to construct a family of non-commutative rings. Okay. So, but let's see. Okay, but I will need these two functions. So I have these two functions to see. So these are merely the projections to the first and the second component. Okay. Now, so I have, okay, so let OT2 be the subalgebra of C infinity functions on the torus generated by 1, Z1, Z1 star, Z2, Z2 star. Okay. So any element in OT2 will be a polynomial in 1, Z1, Z1 star, Z2, and Z2 star. So I have this star operation from O T2 to itself. So which sends F to F bar. So F bar of xy, so this is equal to F xy whole bar. So F takes value in the complex plane. So all my functions are complex valued. Okay. So fxy whole bar makes sense. Now, given this, it is easy to check the following. That so Z1. So these are all unitaries, and of course, so Z1 and Z2 commute. So this multiplication is the operation of pointwise multiplication. And of course, they commute. So the reason I wanted to introduce this all these trivial notation is to just attract your attention to just these three equations. So these three equations say something very simple. So you take the algebra OT2, it is generated by Z1 star, Z2 star, and it has these three relations. Okay, so here is the definition. So this will be this guy will be denoted by O of T2 theta, where theta belongs to those 0, 1.
Z2 star Z2.
Oh, yeah. Thank you. Yeah. So right. So O T2 theta is the biggest algebra generated by UV, some symbols such that A. So U star U is equal to 1 is equal to U star. B, V star V is equal to VV star. No surprises up to here, but then I have this condition. Okay. So if theta equal to 1, you actually yeah, I think sorry. So if theta equal to 0, you actually get back O of T2. The algebra becomes commutative. Okay.
Q is
Huh?
Q has appeared. It's called Q.
Yeah. So, but yeah. So Q will, I mean, would have appeared in another example if I had more time. But at the moment, you let's be satisfied with the theta. So so the point is that yeah. So note that O T2 0 is actually isomorphic to O of T2. So the isomorphism is just given by U map to Z1 and V map to Z2. So this is one example where I am getting a new non-commutative ring by twisting the by twisting the defining relations of my classical ring. So before I leave, let me So let me just show this particular example. So, or should I wait? Are there any questions about what I said before? Oh, sorry. Yeah, sure. Oh, so actually, so I have an isomorphism between the OT20 and the usual functions on the torus. This isomorphism is actually given by U map to Z1 and V map to Z2. That's what I said. Yeah, I mean because so this is just a map between the function algebras on the right hand side. There is no space on the. I mean, when theta is actually non-zero. Okay. So can we move on? Okay. So I mean, so where this comes from? So it comes from the following recipe. So suppose, yeah. So this is for our colleagues. So suppose I have a Jyotishman sister algebra, and suppose I have a compact abelian group G, and suppose gamma be the yeah.
Functions with values in this one.
Sorry.
There are functions with values in this one.
Okay, so OT2 theta is just a notation. There is no underlying space called T2 theta. I am defining a new ring.
So if theta is not zero, it is necessary.
Exactly, but also in that case, if there is no underlying space, I only have the ring. Yeah.
Is there always doesn't always exist a homomorphism from OT2 theta to OT20? I mean, just sending the UVs to.
No, because yeah. So on the left hand side you have UV equal to e power 2 pi I theta VU, right? So yeah. So OT20 is commutative. So yeah. So
not isomorphism.
oh, so just a ring map.
Yeah. The ring map would exist with theta dash.
Well, I mean, so a map you can always have, right? So just send U to Z and V to 0.
Oh, okay.
Yeah. I'm so.
Okay, not.
But what's interesting is that, so I think so you can have a surjective map from OT2 theta to OT2 to theta.
Oh.
Yeah, I think so. If you map U to U square and V to V square, so that will give you a map. Those kind of things you have. So right. So where does this come from? So suppose I have a compact abelian group acting on a Jyotishman sister algebra, and suppose I fix a two cocycle on the on gamma. So out of this data, I can actually define a new algebra A omega. So I mean, two cocycle is something. So it's a map from gamma cross gamma to S1. Now in the particular case of the non-commutative torus, my A was T2, G was T2. So T2 acts on A by left translations, and then I actually use this picocycle. Okay. Okay. So this was right. Now, okay. So let me get back to.
Is it easy to see that U going to Z1, D going to Z2? Beginning you said that's an isomorphism of underlying vector space.
No, actually, what you need to do is that, so that's what I've been suppressing. So all the examples, well, I mean, so at least the example of the non-commutative torus. So I wrote that so largest algebra. So that has to be made precise. So that is made precise by going into the definition of a universal sister algebra, and so yeah, so
it has to be sister algebra.
Exactly, and then so inside that algebra, so if you look at the dense algebra are generated by UV U star V star. So that's my ring. And then so if you so what you can prove is that the full sister algebra of the non-commutative torus at theta equal to 0 is that's actually isomorphic to the full space of continuous functions on the two torus.
So you complete it all.
Yeah.
Other you're working with Lorem polynomials, right? So,
yeah. But I mean, non-convergent. Okay, so let me just quickly sort of recall what I mean by differential calculi. So suppose S surface. So recall that the set of vector fields, this is equal to the derivations of the ring say infinity S. Okay, now what I will need are some objects called differential forms. So suppose my surface is of dimension n. So then I actually have omega 0, omega 1 up to omega n, and all my so omega m equal to 0 if m is bigger than n. Okay, so my omega 0 is just defined to be say infinity S. Omega 1 is defined to be the are we good?
I don't know what happened. Yeah.
and
8907.
Is it over here or what?
10.1.
Where do I put it?
Yeah.
Okay, what's the number? Enter power.
8900.
Say that again.
8900. There is a passcode there. If you put your mouse, the cursor you can go to this one. It's not.
Yes. So
I think it's IP.
should I do something?
No,
No, no.
just laptops.
Does it try IP 10 point? 1 point.
No, this is it's saying password.
Password.
That's a different.
This is 892.
Call the guy. You put host name or IP. No point.
It will surely come back after some time because the current goes on and off. So
No, but nothing happened. So then there was some other problem. Which was
Starting the lecture. No, this is this.
oh, acha. So I should log off.
no.
No. Are you using a browser? In the browser, you type the AP number 10.1. And then you put the.
But he's not. It's my screen which is.
Yeah.
At your screen, is it connected to Wi-Fi or the HDMI?
It's connected to Wi-Fi and HDMI.
See, that code is perhaps 2021. That's to this access that terminal. That's different. But here it's Wi-Fi connected. You have to do it.
Let's just call the IT guy. Are you guys calling? Huh?
On the IT. It's saying download.
No, this was always.
I know they're doing some electrical work outside. I think it might have something to do with.
Electrical was on the Wi-Fi.
Okay. So it's still saying that I'm live.
Yeah, you are live. It's. I mean, people
so-
outside are seeing it, but we can't see it.
Oh,
I mean, this is how you're looking. Oh, now it's come. Okay, great. Maybe it was a good idea to move things around. Sorry about that. Okay, go ahead.
Okay. Yeah. So I need to sort of define or recall what are called differential forms for a level surface. So these will be some modules over the ring say infinity S, and if the dimension of the manifold is n, so then this omega m is 0 if m is bigger than n. So I will just define omega 0, omega 1, and omega 2. So the higher forms can be defined similarly. So omega 1 are actually the set of all C infinity linear maps from the vector fields to C infinity S. Okay. And so omega 2 can be identified as, well, so set of all Fij omega I tensor omega j, Fij belongs to infinity S. Omega I, omega j are one forms, and Fij equal to minus Fji. Okay. So these are the antisymmetric two tensors. Okay. So moreover, what I have, okay, so yeah, so right. So I will ask you to observe that, so chi s, so omega 1s, omega 2s are all infinity s modules. I mean, suppose X is a vector field, okay? So and F is a smooth function. So then basically, XF at the point P is actually defined to be XP times F of P. Okay. Okay. So similarly, it can be easily checked that the one forms and the two forms are all modules. So what I have is the following. So suppose S is an n surface. So have then number one. So there exists infinity S modules omega k. So k is equal to 0, 1, 1 to n. So there exists a map from omega k tensor infinity S omega L to omega k plus L. And also a map D from omega k to omega k plus 1 such that A, so D squared equal to 0 and B, D of omega wedge eta is equal to D omega wedge eta plus minus 1 power k omega wedge d eta if omega belongs to omega k. This can be easily checked and we have this. Okay. So this is the classical stuff. So now suppose I am given a non-commutative algebra. So what to do? So here, in order to define all this, so the starting point was vector fields, right? So why don't we start by defining okay, so suggestion. So what are vector fields for a non-commutative ring? So guess, well, sorry, there's a question. So guess is that, so take, okay, so let's call the ring A. So take chi A to be the set of all derivations of A. Okay, so this matches with the classical situation. Trouble is, so if A is non-commutative, so this is not an A module. So this doesn't work. However, so we will take this theorem. So we will take this theorem as the starting point for the definition of the a differential calculus. So in other words, so here is the definition. So suppose I have a Differential algebra. So our geometric data will be so this triplet. Okay. So omega dot A will be an A bimodule. Means that it's both a left A module as well as a right A module. Yes.
Definition of derivation in case of non-commutative would be?
Oh, so same. So but d of AB is equal to dA times B plus A times dB.
Okay.
Yeah.
So then,
Yeah. So there's no problem there. But yeah, but it doesn't form a module. It's only a module about the center of the ring. So if your ring has no center, then you're in too deep. So here the data is given by a triplet. Oh, mouse.
No. This is something here. Hmm?
maybe it's from there.
Which
Where it's going into the wall.
Probably it might go from here, I think.
Hmm?
Squeeze, but
that's what we did last time.
yeah. You want to consider?
What is this? This is to connect to HDMI.
I think that should all.
Yeah.
Oh. Yeah. Okay. So we were discussing what's meant by a differential calculi for a non-commutative algebra. So it is actually given by a triplet. Wait, I think I should. Maybe some loose connection. Yeah. So
Are there some natural examples you get non-commutative rings from you're trying to replace C infinity of S with
right.
so what other stuff is in the manifold?
Okay. So as I said, so so suppose I have a compact manifold M. Okay. So then suppose a compact abelian group acts on it. Okay. Then and if you fix a two cocycle on the dual of that group, then you can actually deform the algebra CM into a non-commutative algebra.
The mic is here.
Okay, so so not only with torus, but you can do it with any management. In fact, any topological space. Right. Yes. So okay. Yes. So for example, my T2 is a Lie group, right? but I applied this Riffel machinery to it and got different. So if my omega is trivial or like or cohomologous to a co-boundary, however, so then the resulting deformed algebra will be isomorphic to the original one. Sorry,
You said take an abelian group compact.
Tell you what, you just connect this directly to this thing.
Yeah.
Does he have a?
but you well actually
In my
Where is it? It's a value.
in the circle. But I mean actually so there has been a lot of progress after Riffel. So now I mean so the same process holds for any sister algebra and any globally compact group and any cocycle. But I mean so as you can see, so continuously I am working with a unital sister algebra. So that's why I took the group to be compact and yeah, and to keep my matter simple, I took it to be abelian.
Okay, let's hope this works.
Huh? Yeah. It works. Can you hear me? Someone is talking, is it?
That's you only. It's coming from here, the voice.
Okay.
Yeah, just continue.
Yeah. So basically, I have a bunch of A bimodules where omega 0 A is actually equal to A, and okay, so all these omega k's are both left A modules and right A modules. So in the classical case, a left module is the same as a right module, but here our left module structure does not automatically give a right module structure. So that's why I need to specify both the left and the right structure. And just like sorry, so just like before, I postulate the existence of a wedge map and a D map. So D square equal to 0 and this, so this same thing. So this is what I mean by a differential calculus on a non-commutative ring. Okay, so since my time is up, so I will just finish by giving the example for the non-commutative torus. So remember that okay, so what do I need? So the data was a triplet. So my I need to define omega k, I need to define wedge, and I need to define D. Okay, I am going to give you the final answer, but it's a well, so this particular construction comes from somewhere, but okay. So let's start with the space of forms, so omega k's. So the one forms are actually like this. So basically, one has to remember that the two torus is actually a two-dimensional manifold. So the only forms which survive are the 0, 1, and 2 forms. Okay, And so since it's a two-dimensional manifold, so that's why you can see the C2 here. Okay, and okay, and so the bimodule structure is actually given by this equation. So the two forms is just so just like the classical case, meaning that theta equal to 0 case. So this is one dimensional, and all the higher forms are 0. Okay. So okay. So in order to explain the D map, so some little work has to be done. I need to define what I call the square integrable functions on the non-commutative torus. But maybe I should stop now, right? So I hope I have been able to.
So maybe questions you can take.
Yeah.
Any questions?
How do you define the D?
Yes.
Well, thank you. Okay, so what we need to remember is that so in this realm, so the analog of measures are positive linear functions. So by positive I mean functionals such that tau x star x is always positive. Okay. Now I have this particular functional tau, and so basically I can use this tau to give this O, to give this this thing a pre-Hilbert space structure, and then I just complete it to get some Hilbert space. And so then double this Hilbert space, and you define this small d from the 0 forms to 1 forms by this formula. And so here, so mu means the multiplication by u. Okay. So and I similarly have dv. So then from here it's clear that the space of 1 forms is actually generated by by f1. So I don't know if I can make it precise.
One slide. So first, when you take the tau x star x with the summation AMN thing, assuming that M and N are running over infinity many objects, so you would get an infinite sum.
Yeah. So
and you want to put some restriction on the infinite.
So those are the square integrable functions. So L2 means that the tau of x star x is finite, right? Yeah. So basically, I should just explain. Okay. No, I have not defined the spectral triplet yet. So otherwise, I could have shown that So how does one get into these Ds? These are these small d. So one one starts with a spectral triple, and yeah, from that one actually defines what the one forms are. And if you run that computation here, so then you will see that you get the formulas for du and dv as here. And since the algebra is generated by u and v, so the space of one forms will be spanned by du and dv, right? Yeah, yeah. Right, right.
So there you see the, for example, that is committed. So you take a finite group. What is the structure?
Yes, the same thing will work. So yeah. So basically, so what you need to do is that you need to the only thing which you need to have is that the dual two I mean, so there should be at least one non-trivial dual to cocycle. So once you have it, so then typically the deformed algebra will be non-abelian.
You are deforming the algebra T to the standard thing by the two cocycle and getting the.
Yeah, yeah.
So there is no concept for deforming the exterior algebra. The same two cocycles.
Yeah,
is that
then,
how you are getting this formula?
Yeah, exactly.
So there is a concept of deforming the
right,
exterior algebra.
right. So actually,
no, but then the theta disappears completely out here. You are getting only elements of order 2 and but that is for D, is it?
Yeah. And then so if you if you take the two forms and so on, so all these multiplications will start to appear. But so in the case of the refill deformation, the entire geometry with the one forms, two forms, and so on, so everything can be deformed.
But the way you can deform the n forms is once you deform the manifold, then the algebra, whatever, then there is only one way of deforming the
Canonical.
So this one is there are not many choices for your differential patterns. Is there
No,
only one choice for
no. There are plenty. So yeah, but I am talking about this. So this particular Cohn-Landy deformation of a classical spectral triple. So that gives you an algorithm. So not only the algebra gets deformed, so the original geometry you can also deform it, because so basically once you have the group action on the space, so you also have the groups acting on these forms, and so basically it's just the deformation of bimodules. But also you actually need some more conditions. So basically so this particular action needs to be isometric, then everything goes through. So once you have a T2 sitting inside your isometric group, then everything goes through.
So slightly puzzled. You have 0, 1, 1, 0, 0, I minus I 0. So there is this dropping the symmetry between Q and B.
Oh, so okay, but actually, I mean, these are not really. I mean, so actually, so these. Sorry. Yeah. So that's what they are. So actually,
I mean, not exactly poly. So 0, 1, -1, 0, and
Well, but actually, there is a so this particular D, I mean, comes out from of a particular construction. So I can so if you just give me a minute, I can show you.
I think they might be kicking us out.
Okay.
Oh yeah.
We can just take it outside.
Yeah.
Let's first hang the speaker.
Yeah.
We can't escape.
I